Ladies and gentlemen, ladies and gentlemen, welcome to this very special physics colloquium. It is my very great pleasure to welcome Professor Dresselhaus as a speaker to our today's physics colloquium. She has been in Zurich now for the last 3 days, and it has been a great experience to have her around and to learn about her deep knowledge about physics. So an introduction to Millie Dresselhaus could be a talk in itself. And I will try to make it short, and I will just tell you numbers to begin with, because she's an incredible person and an incredible physicist. So she has more than 5,000 citations to her papers per year. And if you check her up on the Web of Science, actually she increased by 500 in the last 2 years. So this is a ramp that has been going up for 50 years, and it keeps going up. It's a very impressive thing. She has an H factor of 101. She was the first female professor at MIT in the physics and engineering domain. She has received so many prizes that I won't tell you about all of them, just a few at the end. She has had more than 100 PhD students, 20% were females. She holds about 30 honorary degrees. It's not exactly clear how many. It's of the order of 30 at this point. She has met all the US presidents since Jimmy Carter. And maybe I can just tell you one thing that she told me. She met George Bush Jr., and she said he was a remarkably uninspiring person. So President Clinton appointed her to be Director of Office of Science of DOE. And of the last 2 prizes that she received, so the last one was the Fermi Prize, which is a big prize in the United States. And this she got from President Obama. And if you check the web, there's a very nice picture of Millie Dresselhaus standing there with a big smile, and next to her, President Obama with a bigger smile than Millie's smile. It's worth looking at that. She also received the Kavli Prize for Nanoscience in 2012, and this is the biggest prize in nanoscience. It's considered the Nobel Prize in nanoscience. So, and you can tell from what I just said, there are many more things to be said, but we are really here to listen to her physics, and therefore I just want to add 2 small things that tell you a little bit about her character. I put these numbers together and I asked Millie about them, and she said, oh, you know, these numbers are not really important. What matters is good science. I don't know about these numbers. And I think this is really what you learn when you talk to her. It's all about good science, and these numbers are not so important. So she's a very busy person. So we wanted to treat her to dinner tonight, but she said no. She has a busy schedule, so she's going to take a plane tonight to Brussels. She's going to take another plane tomorrow to Hamburg. Then she's going to take another plane to Boston. So she's very busy, and we couldn't treat her to dinner tonight. So we treated her to dinner yesterday. And I made her 2 offers. I asked her, either I take you by taxi to the dinner, or our department chair takes you in its BMW sports car to dinner. What would you like? And she said, oh, I'll take the sports car. Okay, Millie, it's so great to have you here, and we're looking forward to your talk.
Well, thank you for the jokes. I was amused myself. No, I really don't know the numbers, and I don't really care about them. But, you know, perhaps when you're young you care about it, but I never did care about it. So I'm still here, so still working. You know, that's the important thing, to enjoy what you're doing. So today I'll talk about 50 years doing nanocarbons. So why do I do this? Again, because I really enjoy it, and I hope that you'll enjoy nanocarbons too. So this is me 50 years ago, actually. I thought that it would say 50 years ago. And that's the way the labs looked. Pretty different from today, huh? Even way we dress has changed quite remarkably, laboratory attire. So, okay, so that's for your amusement. And now I'll say something. So the field that is really a little bit older than 50 years. And so this is 13 years before. And I was inspired when I started my independent career to do something that was different from the other people, just to entertain myself, really. So I was looking for something that had some kind of different electronic structure. And so you would see here that there's a linear E versus K. And in condensed matter physics, this is very unusual. And maybe at that time it was considered even more unusual than today, because there was nobody in the world interested in carbon, pretty much, as I'm going to show you in a moment. But I was interested in this, and I wanted to see if I could figure out why it is that everything else had a quadratic E versus K, but this system is different. So what's different about it? And I'm not sure I completely satisfied myself in explaining this, but in the process of looking for new science, you do find it. So there's just a ton of new science, some of which we've discovered, but there's just so much more for you guys to find. So, and this is almost true of every PhD thesis. I'm on many thesis committees besides my own students, because at MIT students can select their committees, at least to some degree. And so I enjoy hearing all the different theses from different academic departments. So, well, anyway, today I'm going to tell you something about the carbon field. So starting in 50 years ago, so that's 1960, and that was the year I started my independent career. So this is number of papers, and this is time. Almost nobody was interested in this field, and that continued for 30 years, pretty much. Very, very little interest. And then the Fullerenes took over, and then nanotubes, and then graphene. So this revolution started not so long ago, and one thing triggered the other. Because of Fullerenes, we had a number of people that understood something about nanocarbons. So when people got excited about nanotubes, so they jumped in, and then graphene, they jumped in. But new people came also. So that's what we see here. And I will follow this thread over 50 years. And so why am I doing this? Well, I was thinking to myself, there are two reasons. People like to have me give conference summaries, so this is sort of conference summary. And the other thing is they like to have me think about what we're going to do next. And I'm not sure I'm going to say very much that will inspire you. But the one thing that comes to mind in looking at that past 50 years is most of it was done without thinking of nano. And almost all the topics that were touched in the past, say starting the last 40 years, have not really been revisited. In the last few years, we've looked at graphene. So graphene also started in this early time, and it's exploded. But all the other topics have had very little attention. So you might pick up some interesting things listening to this that will catch your fancy. And so that's one of the reasons that I'm talking about what I am. So this is now 50 years ago when I started. So this is work on graphite. And believe it or not, 50 years ago, we knew very little about the electronic structure of just element carbon graphite in the most common ground state configuration, sp square carbon. And the experiment that I was involved with at that time was magneto-optics. So we have a light beam coming in on a graphite sample in a magnetic field, and we look at transitions between valence levels and conduction levels. Very simple experiment. It was done with a laser. It's the first laser magneto-optics experiment. Not only that, it was done with circularly polarized light, and the first experiment done with that. I wasn't the person that made that. That was done by Ali Javan, so he's co-author on this paper. And on this particular work, it was really the most fundamental thing that we did in the 10 years because it elucidated the fact that up to that point, and this is many years, people had misunderstood electrons and holes and misidentified them. So by doing the circularly polarized light, we can tell what size the electron, rather than the hole, was rotating in a magnetic field, and that gave the sign of the charge. And that showed that these pockets were electrons, which previously had been thought to be holes. So this is a kind of interesting experiment. And this is the beginning of my career as a professor at MIT. This is the first work that I did. And it was done with Ali Javan, you see there, and Paul Schroeder was the graduate student, his PhD thesis. So that was a kind of fun experiment. I really enjoyed, we all enjoyed that experiment. And I was getting back to carbon and graphite. It was always interesting to do experiments on single layers, but nobody knew how to do it at that time. But we had the idea, and that came from the work at Bell Labs. Bell Labs was a research lab at a company, but they had really great people, and they were doing wonderful work. And they started doing research on intercalation compounds in 1965. And they kept talking to me, asking me to join them on a project. So I did after a while when I could figure out what to do. Then we studied this intercalation compound. Let me explain intercalation compounds. So this is a single layer of graphite. So graphite would be this layer, that layer, that layer. But the layers actually are separated from each other by introducing a chemical species. And that's how we make the single layers. And the chemical species is an alkali metal. It could be any alkali metal, but potassium was chosen for this particular case. So that produces this sample. And then we're going to do many, many experiments on this. And well, I think I must have had 15 PhD students at least getting degrees because we examined this for many different materials. That is, we could put many intercalants in. And we could have many numbers of layers, 2 layers, 3 layers, 4. So it was all pretty interesting. This was done for the infinite lattice. Now, nowadays, we know how to make small pieces of this. So all of this work can be revisited with making few-layer graphene. So when you look at this old work, you see new possibilities to bringing this to the present nano world. Okay, so what did we find? We found that a single layer separated by intercalant, so that's C8 rubidium here. Rubidium is the intercalant. That looks pretty different in the Raman spectrum from 2 layers or 3 layers. You could see line shape, line width, everything's different. So a single layer at that time, we could make isolated single layers. That looks different, so that's intriguing. And of course, if you're looking at a system like this, you want to see what happens to what goes between the layers. Well, a single layer of rubidium we couldn't do very much with at that time, but we could do something if we put other materials in between. So this is bromine. And with bromine, this is bromine lattice by itself. When it goes between the layers, it retains the same kind of crystal structure, but the lattice constant changes dramatically. So the separation between the bromine, the 2 atoms of the bromine molecule changes. And you get a really beautiful spectrum of the vibrations of the 2 atoms going like this. And the frequency is different from the free atom by 50%, 50%, big difference. And that's done by the carbon layers. Amazing, isn't it? You wouldn't expect that. So Intercalation is interesting today. It's the basis of batteries. Put in lithium between, and then we harvest energy. And there are people doing work on that right here at Zurich, so ETH. So there are lots of people knowledgeable about this. So that was kind of work in the 1970s. And it continued into the 80s. But I started some other things during that time. If you take a carbon surface and you have a laser come out, things come off it. If you have enough power coming in. And so I was expecting C2, C3 maybe, but big chunks came out. Our clothes got dirty, so we knew that there was big chunks of black stuff coming out. And what was that big chunk of black stuff? Well, people at Exxon were specialists in this, and they had gone up to 15 carbon atoms in a ring coming off the surface. But the amount of energy that went in was very little, and the size of the clusters was large, just judging for how much carbon was expelled. So we knew we had big chunks, and so I went to Exxon and said, please try to extend your experiment, which they did, and they got this spectrum, and it shows there are lots more chunks that you can have clusters, but the clusters change when you get above 40 atoms per cluster, and they become separated by 2. There's something funny going on, and there's a big one for C60 and C70. Well, we couldn't figure out, they couldn't figure out, but it was Smalley that figured this out, and that was the Fullerene. So that started Fullerene physics. And so that's the first really large man-made molecule. It's, of course, in outer space has been found afterwards, but this was on Earth, the first one. So this really started a kind of part of nanoscience in the mid-'80s that built up a large number of people with interest, and there was a lot of physics in this. This book is very fat. It's about 1,000 pages. And we started out doing spectroscopy, and we thought it would be a thin book. But then we got more things, and the amount of material and information was way too much for papers, so we made a book. And so this is just full of spectroscopic information that you get from clusters of atoms of different size. And so the simple spectrum of fullerene, this is just C60 that I'm showing you here, but it could be more things that this is a beautiful molecule. It has so much symmetry. So because it has so much symmetry, you can have a zillion modes. And so the number of different modes in the second order combination of modes, take direct product of all the possible combinations you can get. There are 200 of them. And it's amazing that the prediction of the selection rules, of course, is very high symmetry, so that there's a lot of information on the selection rules on them. It's not everything that can be for this and that polarization. And it works out beautifully when you do polarized light. All of these things can be explained, predicted what the symmetry was. So this really was a wonderful example for my group theory class, to see that how group theory works in a complicated molecule like this. Okay, so that was work in the 80s. And another thing that we were doing in the 1980s were carbon fibers. So this is a book that we wrote. It came out in 1988. It's not available anymore. It was sold out a long time ago. But people that have it like it because it has a lot of information. It has a lot of information for me still, because I don't know where to find it elsewhere. Maybe Google it. But it's a very useful book. You probably have a copy in your library. We have, I think, 2 copies at MIT in the library. But it's hard to get them because they're, for some reason, often in use. Okay, so carbon fibers was a very interesting topic, and it came as a result of a conference on intercalation compounds, which was international, and the Japanese came, and a young person called Morinobu Endo came, and we met for the first time at the conference, and we became collaborators back in 1980, so that's 40 years ago. We've written many papers together. So, and he's been a person that's been in my applied side. Many applications of carbon come with him. Okay, so that's, now getting back to what I was doing, and 1990, important thing happened. There was a conference in Washington, D.C. I was invited, and Richard Smalley was invited. And I was invited to talk about this subject, and Richard Smalley was invited to talk about this subject, C60. And we were the two invited speakers. And at one point, they put the two of us on the stage, and they asked us, what is the relation between fibers and C60? Well, it didn't seem like a whole lot, because carbon fibers are kind of macroscopic, but they have microscopic content. And so anyway, we fantasized, and you can go from C60 to C70 to C80, and get elongated. And so there's a fiber. The simplest fiber you can have, 1 atom thick. Would be nice to have this. And then eventually you get the filaments and the fibers. So that's the connection that we fantasized. And so I was thinking about this, and I mentioned to a few people, gee, it would be interesting if we could make it. I wonder what the properties would be if you could make it. So it happened, this is 1990 now, that the following fall, I had 2 young people just finishing their postdocs, Saito and Fujita. Some of you know them. They visited to do a year's sabbatical at MIT. And they came to see me very soon after they arrived and asked me if I had some suggestions of interesting problems that we came upon in our experiments. And I mentioned to them, suppose you could have a single-wall nanotube. Would that be interesting from a scientific standpoint? That was the question I asked them. So they said, we'll look into it. And so they came up with the idea that it would be very interesting, because if you could do that, the nanotube that you would make by rolling up a single sheet could have a characteristic that it could be either metallic or semiconducting, depending how you rolled it up. So that seemed like a pretty interesting idea. So we wrote this up in a paper in 1992. And just around the same time, 2 other groups had the same idea, independent. We didn't know about each other, but so there were 3 people that had the same idea, and they came up with the same result. That's pretty good. We have 3 groups agreeing on something. But what we came up with is that this could be either metallic or semiconducting. And there weren't many people in the world that were ready to accept this, so this became a very controversial topic. Today it's not controversial, of course, but at that time it was very controversial. And so the argument that we use is just simple physics. So if you have, in carbon, you have this Dirac cone, so that's a 2-dimensional system that describes the electronic structure of a single sheet. And if you roll this up, the number of atoms around the small cylinder will be a small number of atoms, and you could only have states corresponding to the number of states corresponding to the number of atoms. So we'll make these cutting lines, and the cutting lines are these singularities, Van Hove singularities, in the density of states. So they make a very high density of states right at the cutting lines and no density of states at all elsewhere. However, if one of the cutting lines went through this apex, then we had touching, conduction, and valence band, that's a metallic state. Or otherwise, if they didn't go through this apex, so there would be a band gap. So we have those 2 possibilities, and so that's the physical basis of this idea. It's so simple that any undergraduate in the solid-state physics course nowadays can understand this and accept it. But it was controversial at the time. If you're unfamiliar, it could be controversial. So that was the prediction, and then we did some various experiments and showed that that was correct. One of the techniques that we've been using in this in these studies over the years is this light scattering. So in a light scattering experiment, inelastic light scattering, experiment. So you have light coming in with some frequency and wave vector, and the scattered light comes out some other angle with some other frequency and wave vector, and then maybe a phonon. It changes takes place as the difference between these two frequencies, and that's the inelastic light scattering. So the phonon that's created could be, here's the phonon creation, or we could have the phonon absorption, either way. So phonon frequency can go up or down, and so we have both possibilities, and they can be observed experimentally. So, so here is some examples of what we found. So on the left is bundles. So we have a whole collection. When the nanotubes are made, or at least in 1997, this is the first experiment, the major experiment in the field, we had a bundle of nanotubes, and they all had different chiralities. So because of that, you have there's no systematic. Every frequency shows different, we always have a resonance showing that there's some nanotubes that are resonant at that laser energy, but then there are other nanotubes that don't contribute. And then we have this new feature, and that's the vibration. We have the nanotube, and it's going in and out breathing, and that forms vibrational frequency depending on the inverse diameter. So we can measure the diameter of the nanotube with this frequency and get information about the interaction, the scattering of this wave vector from this higher frequency. So that's what the physics is of this spectrum. So this is 1977 work. And, but then we had, since the spectrum was so strong, we said, well, let's try one nanotube, and that's shown here. So here are our nanotubes, and then we spread them out and just collect one light scattering from one of these tubes. And we get different spectrum if they're metallic or semiconducting, and this is from one tube. And the spectrum for every tube is different because it has a different chirality. And that was the first way that people were able to identify chiralities of nanotubes. Of course, we have many ways now, and we can make nanotubes on demand, the companies that do this. But this is just about 15 years ago. So progress is made. What we're doing nowadays, I'm giving a talk on this because the student that, I had a visiting student that was working on double wall nanotubes, that's shown over here. Now the next few graphs I'll show is triple wall nanotubes. So this student was first guy doing triple wall nanotubes. But double wall is enough. So you could see that, oops, I didn't want to do that. Let me go back. So double wall, we could have metal semiconductor, et cetera. 4 possibilities, right? 2 times 2. And each of them had different properties. And then you can sort of telescope them, move one inside the other. So you have really quite a large variety of spectra. And for the inner tube, it could fit into a different bunch of outer tubes with slightly different separations and diameters, slightly. So different forces, therefore different vibration. So there's a very rich spectrum. And so we're studying this in some detail. That's his thesis. And but really his thesis is this, because a number of papers have come out already on double wall, but this is first one on triple, so that thesis should be original and new. So you could think about this as having a double wall tube surrounded by another kind of tube that's either metal or semiconductor. And if you do that, you can really make quite a lot of progress in systematizing the spectra that you get. That's an easy way to look at that. That was a way that he was looking at it. There are various features in the Raman spectra, and he looks at a few of them. This is the master's thesis part. The PhD, you can look at the other ones. So there's a lot more for him to do if he likes it. Okay, so this is the way research develops, and you learn lots of things. And once you get all this experimental results, you're going to have a lot of theory to try to figure it out. So samples are kind of beautiful. I think they are. So here's double wall nanotube. Triple looks about very similar. And you could see these. This is a bundle. That's how the ensemble looks. And then we separate in individual ones. And we do spectroscopy on just one double wall nanotube. So that's what the thesis is about. And so we could look, the bundle, we have a mess, you know, everything is within every other line width. But if we look at the individual level, we can identify the individual tube. And then we could look as a function of laser excitation energy, so we get a lot more information. And then we also put on gates, so we change the Fermi level. So we have a lot of different data that we can look at and learn all kinds of things. So that's sort of an idea of some of the things that we're doing with nanotubes. We're doing a lot of other things with nanotubes, but that's a good summary. Now I'm going to say, so nanotubes is here, and now we say something about the graphene world. And I'm not going to say so much about graphene because graphene is very popular in Europe now. They have the flagship program, and €1 billion invested in this research. So there'll be a lot more information coming from Europe, from this program, I imagine, than anything from the rest of the world. So we'll leave them to talk about it and tell us more about the nanotube. The graphene starts in, this is here, 1962. So that's 50 years ago, exactly. And Hans-Peter Böhm is still alive, and he's exactly my age, within 1 or 2 months. That's surprising. And we made contact. I hadn't seen him in a long time because he's not traveling nowadays, but I got in touch with him. We had a conversation, and so he remembers me, and he was very happy that I'm still working. So, well, I guess in Germany it's more difficult to keep working after retirement. So, okay, so here's a single layer of graphene, and we have 2 atoms per unit cell. And then we make bilayer, we stack them. The A atoms go above the A atoms on the next plane, but the B atom is staggered. On the next plane, it goes at this position. So that's, we call that AB stacking. And then you could do 3 layers, and you do ABC stacking. So you see that their AB stacking would make, when it's in this position, a 30-degree angle with this. But then we can go, and the next layer, you can put the atom over here. So we can make like a spiral going like that. So that's ABC. So that's different stacking orders. Stacking order is important in graphene. Now, here is single layer, and here's bilayer. This is energy dispersion. Okay, here's the linear E versus K, right around the K point where the degeneracy happens, and we have the cones, Dirac cones, and all that. And then when you make bilayer, it's almost the same, but it's quadratic right at the point. But it's amazing how similar this is. People don't often recognize that similarity, but it's very, very similar. But the properties are different because just at that point, the dispersion relation is different. And that makes quite a large difference because it's a breaking of symmetry, and symmetry is very important. So let me just emphasize that. And so there are the bilayer. So we have a band gap between the first and the second layers. Okay. And now how this is made. Yeah, we're peeling graphite from the earliest time. I'm pretty sure that in 1947, when that paper was written, people started peeling graphite. Because I know in 1960, we did this every day. But nobody thought of making 1 layer until 2004. So it's very, very, sometimes you have great science right in your backyard, and you don't do anything about it because you don't think of it. So this is a very simple, like we call it the Scotch tape trick. And so they took Scotch tape, actual Scotch tape, that you all know what it is, and put it on this messy little piece of graphite and pulling off little, one layer at a time, repeatedly, until you get just one layer. So this is, you could see, you're getting thinner and thinner, and now you could see 1, 2, and 3 layers. So that's what these guys did. It was very ingenious, very simple, and they absolutely deserve the Nobel Prize for doing such a clever thing, but not only doing the clever thing, but finding out some very interesting physics about it. So, so there are some of the samples that they made in the early days. We call that the Scotch Tape trick. I think they called it that. And the paper that attracted everybody's interest was the quantum Hall effect, which is different for graphene than for gallium arsenide, for example, just ordinary semiconductors. So this attracted a great deal of interest and attention. So some of the remarkable properties, it's the thinnest sheet because it's just a single layer, only surface. So it has a huge surface. That's, if you want something with a lot of surface, that's it. And zero band gap because you have this degeneracy, and high mobility. Graphite has a mobility of 30,000, and at least the early work was 100,000, but now people have 1 million, so they say. And the other properties, like superb conductors for many carbons, this is not graphene only, many other have very high thermal conductivity and can carry high current densities. That goes with the landscape. One of the advances, and this is Philip Kim at Columbia, was I think perhaps the first person to do this. Although we knew about HBN for many, many years because it was produced by Union Carbide Company along with graphite, so you could buy it, but it wasn't very high quality. And so recently there's big advances in material science of HBN. I mean, that's my feeling. And a surface of silicon SiO2 that we put graphene on looks pretty awful, but boron nitride is very flat. So Philip Kim was right in doing this, and he got some very beautiful results and a lot of work going on here, making use of the very nice properties of this substrate, probably good for many other semiconductor applications. So think about that. The spectrum of graphene is extremely unusual. So first order, small peak, this is first order light scattering. Second order, huge peak. What's going on? We teach our students, I think that you have, quantum mechanics in second year of undergraduate. So we teach you perturbation theory. Perturbation theory tells us that the perturbation is smaller than the effect itself. So every time we go to second order, third, every order of perturbation theory, the effect is smaller, but not for this. Look, second order effect is a lot bigger than the first order, so what's going on? Well, in perturbation theory, if you have a resonance, you know the second order term has a denominator. And if that denominator gets very, very tiny, and goes to close to 0, wow, you can have a big term. And the reason that that term is so large is because of the linear E versus K. Every point in E versus K is resonant, has a possibility of making a transition. Normally, we only have one energy that's resonant, but here we have all of them. So that's sort of my understanding of why you have such an unusual high-order perturbation theory. And the second order effect is very, very interesting. Second order is, we know, scattering and second order effect. So light comes in, and so that's the first part, and then we scatter from this K point to another K point. That's a K prime point. So there are two cylinders that are related by time reversal symmetry, because this corner and the next corner are related by time reversal. One is K and the other one is K prime. They're not exactly the same. They have all the same spatial operations, but time reversal symmetry is different. And so we can make this scattering event, and then we'll come back to finish the process. So that's the wave vector, because it's wave vector dependent. And then we do it in green light, and we have a smaller wave vector, and red light yet a smaller, so therefore it's dispersive. So we can change everything. That's why these light scattering experiments in carbon, this linear E versus K, gives us two tools. The energy of the light allows us to probe different wave vectors in reciprocal space. So that's very good. We have a nice handle. And then we can change the Fermi level besides. So by putting on a gate, that controls the carrier concentrations for transport properties. So we have lots of interesting things to do in graphene that we don't have normally available. And bilayer is interesting too, as you can see, because you can make transitions from the first to the second, or the second to the second, or any combination, 4 different combinations. And those are the resonance lines. So there are many interesting things to do with the second order spectrum also in bilayer. And then you could study stacking, that's interesting. So many things, many projects. And here's the dispersion relations for each of the 4. You see that they're different, so we could separate them. And that has been studied. And we start out with the first order kind of effects and the second order, but then there are many-body effects. So we can study those because it's such a simple system. It has only carbon atoms. And then, there are the electrons, and the electrons can talk to each other. So this is a great system to study about how electrons talking to each other. The spectrum is very simple. You just have, this one is the lines, the vibration where the atoms going like that. And then we have 2 second-order lines over here, second-order spectrum. We understand those processes. So we have many things that we can study, and then we do this. So this is a little bit complicated, and this shows that we can change the laser energy, and we can change the Fermi level. And when we do this, we get a wave vector dependence. So depending on whether you have a first-order process, then the frequency has a minimum, and the width has a maximum. But now when you do the second order process, you find exactly the opposite. And then trying to understand that has to do with many body interactions. So we've been studying that effect. I'll show you in the next, but not get into any detail. You see that the frequency is now a maximum rather than a minimum. And the line width is opposite in sign also. So this was actually predicted theoretically first, and then we did the experiment. So we learn a lot from theory in carbon because it's so simple. The theorists love to do it. There are a lot of theory papers. This is one field where theory has often led experiment. Recently we've done some work on the combination modes, the same experiment with the combination modes, and the different kind of combination modes are shown. And by this combination of frequency, that's from laser frequency, and the gates, we can actually separate and find out if there's one process or 2 processes. We can tell what combination modes there are. So, like example of that here is this G prime. This was discussed. There were a whole bunch of papers, some calling it this identification of this combination mode, some giving it this kind of identification of a harmonic. And it turns out that they're both right. And you could bring them out by having different combinations of laser lines and the gate voltage. So this is an example of what we've been doing with these peaks, but there are many other combination modes that are seen that are rather weak in the Raman spectra, and each of them have a story. There are really many of them, and each of them have a story that you can unravel with this same technique of laser lines and gate frequency. So that's what we've been doing. I won't bore you with this because it gets very detailed, and this is only good for the aficionados. But I don't really know to what degree this kind of approach is useful for semiconductor physics, but probably you know all this already because it's been studied for a long time. But this turns out to be quite an interesting and powerful technique that for carbon. So I haven't thought about it for other systems, but it might be interesting. I'll end my talk. I won't say anything more about graphene because that's a very heavily studied topic, and that needs a lecture all by itself. So I just talk about ribbons because we've been working on ribbons in the last 10 years, and that's turned out to be a sort of a very much fun topic. So I had a female graduate student that came as a visitor, and she wanted to calculate the electronic structure of zigzag ribbons. So you could see that the ribbon depends on how many rows of zigzags. So there are 5 rows of zigzags. We call it n equals 5. And all of these are metallic because they have a high density of states. But we can make the corresponding thing with armchair edges. And these are 5 rows of armchair edges, so it's the same width as this one, pretty much. And these are different because they can sometimes be metallic or sometimes semiconducting, just like nanotubes. So you could think of ribbons as nanotubes that is zipped open. You cut them and zip them over. And that has been done, and people have made, Hunji Dai at Stanford has made ribbons by cutting up a nanotube, open a nanotube. And so for the armchair, you have metallic or semiconducting, depending on this index. Detail's not important. It's like nanotubes, cut open nanotubes. And so the first calculations was done by this visiting PhD student. 1996 was her PhD. And so she predicted that all the zigzags would have a high density state at the Fermi level. Here they are. They all look like this, high density states of electrons at the Fermi level, carriers at the Fermi level. And then for the armchair, we could have different possibilities. And so here's the armchair. So you could have metallic, here's no band gap, or semiconducting. There's 2, depending on, and then the Berkeley group, they put in spin orbit interaction, made it a little bit more fancy, and so improved the calculation. But they get almost the same result. And some experiments for this, and then I'll have questions. So, so this is about 8 years ago, Inoki made some ribbons, and so we did some collaborative work on spectroscopy. So this is a 2004 version of a ribbon. And so this is about 10 or 12 nanometers wide. Not very good edges, may make much better edges now, but this is old work. And the first Raman work was done with these ribbons. It was very instructive. So there are 2 peaks. The little ribbon was put on a graphite substrate, so we could get the spectrum of the substrate, and that's in full lines. So frequency is always the same. But the ribbon, if the polarization of light is along the axis of the ribbon, then we get a big signal. Otherwise, the signal gets smaller and smaller and follows this kind of polarization behavior. Predicted to have that behavior, and the points are, experimental points are really pretty good for showing this. So then there was theory about the polarization as well. And that was Saito's student, PhD student. And okay, so here is more Raman on edges. So here's an armchair edge and a zigzag edge, so 1 and 2. 1 is supposed to have pretty big D-band disorder because it's symmetry breaking, it's a boundary. And the zigzag boundary is supposed to be 0, but it's not very good zigzag, so it has small. But it's noticeably different. So you can use spectroscopy to determine what edges you have, or you could use STM. So they're different techniques, and they agree. Finally, what we've done is, there was another student that found me at one of the nanotube conferences, and she showed me that she had this kind of material and asked me what to do with it. So I said, come up to MIT and we'll take a look at it and do some spectroscopy. So she spent half a year with me doing part of her thesis on the spectroscopy of these ribbons. And then another student did high-resolution TEM. So this is collaborative work of the two graduate students. I'm going to show you. So to improve the edges, they did Joule heating. And that was the idea of Xiaotung. And so initially, the heating IV characteristic is mostly linear, but then it takes off, and the tube gets very hot and goes to about 2,000 degrees, as we could estimate from putting particles on it. We really don't know exactly the temperature, because we don't have a good temperature scale. The pyrometer is not accurate enough to tell us what that temperature is. So I'll show you later. We use particles, but that's not very good yet. We hope that somebody can help us with that. So this is initial sample, and after heating, you can see a big improvement in the crystallinity of the sample, that ribbon thing. And so here's what we do with the heating. We put the particles on because we know it's getting hot, but we don't know how hot it gets. So we watch these particles first grow, they coalesce and they get bigger, and then they melt. So that both vaporize and they grow, both they sinter, and so it's a complicated model of what's going on there. But so here you can watch them melt. See that? And and this is the microscopy after Joule heating, and we have really very beautiful pattern that you could see in a regular microscope. So we're very, very happy with this, and we have lots of data on what happens with these edges. You can see zigzag edges, armchair edges, and a lot of different things. Here's more edges. You can tell which is, and it's in the beginning. The sample is kind of disordered looking, no clear edges. But after a little bit of Joule heating, just a few minutes, you get nice system. So other groups have tried stuff like this, and it works for them too. So you can do it. And let's get rid of this. Okay, so here are the edges, arrays. When they crystallize, you get more and bigger and bigger arrays as the process goes. You can see here. And so, as far as I know, no theory about the formation of these things, and or the separation of them. They sort of stack in the C direction. They like edges always attract edges. We've looked at many in the microscope. They always like to be near another edge. They like each other's potential, lines them up. So they Joule heat until they get edge formation. And here's the particles again, what happens at different times. You can see them melt. So this is the end of my talk. 1960s, going back a long time, we were studying graphite. That turned out to be pretty interesting. And we were fascinated by that, but then we got into something else, and that sort of took over. 1973 we started, and graphite intercalation. But around the world, it still didn't attract a whole lot of attention. You know, maybe 100 people came worldwide to a conference. I don't think it ever went more than that. And then Fullerenes came. That attracted a lot of attention because it was a beautiful molecule. Chemists joined the crowd. So this made a big difference, Fullerene community. And then when nanotubes came, that was a factor of several more papers per year. And so all these people just jumped into the bandwagon when graphene came along. So, but I don't know exactly what's next. So what's happening in the field? Well, of course, we're doing double-walled nanotubes, triple-walled nanotubes, this kind of thing. So this is more of the same, but studying interactions. So that's interesting, keep us busy for a while. And similar things happening with graphene between layers. That's just corresponding thing. But beyond that, what's happening is there are other layered compounds that are two-dimensional that are interesting. We've known about them for years, but there's been very, very little research on them. And so the chemistry is pretty well developed. It's getting better, of course, now that lots of people are studying these materials. But we don't know a whole lot about them. They have other interesting properties. MOS2 was the first one, and that's a lubricant, and companies making that for lubrication. So it has big commercial interest, but the structure and optical properties is not too important in lubrication. But we'll see many other kind of applications, I'm sure. And then we have tungsten disulfide. That material was known as an optical material also for some time. Bismuth, selenide, telluride, known for thermoelectric application. So we have a bunch of different layered compounds that were known to small groups of people until now, but now lots of people are, if you go, we haven't had the APS conference that's coming up pretty soon. We'll see how many people are in this field, but I imagine it's going to be quite mobbed in these areas. So there's interesting physics, and that across layered compounds has had a revitalization. So I ask what is happening after that? Not clear at the moment. So anybody with ideas? The chemists are making new kinds of layered molecules, complicate things. Germany is very good at that. So we may see some interesting new materials that are layered that will be followed, but that hasn't happened yet. So that's about all I can think of for the future. And I think I have to think of some new things, because a few more months we have the intercalation conference, and they will ask me, what's the future? And I have to come up with some new ideas for them. So I'd like to open to questions. Anybody have some questions? That'd be good. Let's have a question from one of the students, especially an undergraduate, a bunch of young students here. Anybody like to ask something of any sort? Okay, shy people. So let's be.
Okay, here's a student.
Oh.
Actually, one question. Why isn't there more research on graphite manipulation?
Why?
Why isn't there more? Because Fullerenes nanotubes definitely have some carbon, but the application component can't really be jumping up.
Yeah, so the question is, why isn't there more activity in intercalation compounds? Well, I think there will be, but I see papers now and then. I'm a person that gets many papers daily for review, people want. So, and that's a field I'm known in, so I think I would see papers if we had a big jump in number of papers coming into the journals. But there are more papers, but it's not a huge increase. I think what's happening is it takes a while for people to become familiar with the chemistry and how to make them. So if you look at this chart, there's always a delay in the rise of the peak and the discovery. And it's usually about 3 years. So maybe we have to wait a little bit more to see the effect of intercalation compounds. Because I think people are thinking of what new things to do, and that's an obvious thing to do. You're right. But I haven't seen a big, maybe somebody else knows in the audience about that. Yes?
Can you tell something about potential technical applications?
Of which? Of graphene? Yeah, well, if you read some of the advertisement for the flagship program, they have a few pages on no, maybe a chapter on applications. So if you'd like to have a detailed prognosis, the truth of the matter there is that there are two serious applications that I'm aware of. One is conducting transparent materials. That's an obvious one because you can dope graphene. Well, graphene by itself, room temperature, has some carriers. It's slightly conducting, but it's transparent. You can dope it a little bit less transparent, more conductivity, so you can control that. Yeah, so you can make a product out of that, and there are companies doing that. So another thing is that's more complicated, is to make high-frequency electronics, terahertz electronics. We don't have very good terahertz electronics. And graphene, because it's a light material, has very high vibrational frequencies. So it's a good candidate. And IBM has a serious program, but it's just a few people, but it's serious. Very good people working on that. Well, those are two that I know are under development. I'm sure other people know more things about it. When you think of all the remarkable properties that it has, you can utilize them. You know, people use it for gates and in electronics as combinations of things. You know. No companies that I know of yet are doing this, but it'll happen. Yes?
Could the motion of the edges be controlled by mechanical deformation?
Yes.
Could that become electromechanical coupling?
Yeah, so the question is, if you have a sheet, I don't have a sheet here, here's a sheet, and it has edges, so if it's thin enough, it'll be vibrating, and it'll be vibrating more than, now, there's some problems. Right now, the edges normally are not very good. I mean, this is a nice edge. But of a real graphene ribbon that people normally make, it's not very smooth because you have to make the edge sometime. And there are two preferred directions of edges by energy considerations. Those are the armchair and the zigzag. When you make an ordinary ribbon, you won't have that. You'll have some arbitrary direction. So the edge will break up into these high symmetry directions that results in a rough edge. So unless you start out with the right direction, a single high symmetry direction, you're going to get a rough edge. But if you start out with the right direction and you Joule heat it, you should get a pretty nice edge. So there are some examples of people making nice edges, and then taking a nanotube and cutting it open along the proper direction, then you can also make a pretty nice edge. So there's some, yeah, the technology can be developed and the science can be done on those kinds of samples. And there are some things in the literature now coming. And theory, too, is good for that.
So can I ask a question about the nanotubes?
Yeah.
You mentioned that there are these triple wall nanotubes where you have metallic, insulating metallic, and so forth. So can you distinguish for such nanotubes whether the metallic part is in the center or in the middle or outside?
Yes, easily. So what turns out to be, so let me explain. The question was, so we have a triple wall nanotube, and I call them flavors, metallic and semiconducting. So the three have whatever flavors they have, metallic or semiconducting. So because they have different diameters, they'll have different vibrational frequencies. And the vibrational frequency will be within a small range. Right? And in fact, most of the experiments, at least that our group has done, we start out with the inner and the second one made of what we call P-pods. That means that we start with a nanotube and put C60 into the center and then heat that, those two things. That's called P-pod. It has one tube and it has C60. And what happens after you heat this, the P-pods merge and they make a second tube. So we have an inner tube and an outer tube, and the range of diameters of the inner tube from the P-pods is very small diameter range. And because of that, it's very easy to do spectroscopy, and we could, on the individual level, tell the inner one, the middle one, and then the outer one is a very low frequency. That can also be done, but maybe not quite as accurately for us. So we can tell the flavor of the three that way on the individual level. And then we find the student that I'm going to be on the thesis on, today is Wednesday, so it's Friday. I'll be in Hamburg. And he's done exactly that. That was his thesis, to do those three tubes, and at the single tube level. So we can do that, and he doesn't have all the flavors, but he has some flavors. I mean, there are 8 flavors. He doesn't have 8 flavors, but he has some. I think he has 4 or 5 flavors.
Can you intentionally make them metallic, for example, in the outermost shell?
Yes. Yes. You,
By what mechanism?
oh, for triple wall? For double wall, I think you can do. But, well, if you do the P-pod method, you won't get metallic tubes because the frequency doesn't work out. But with another system, the answer is basically the synthesis people now have reached the point, at least with single wall nanotubes, that they can make not every nanotube, but I think there's now 13 nanotubes that can be made at a commercial level of NM specified by you and order. Maybe it costs quite a bit of money to get them, but they can make that for you on demand. They have the formula, growth conditions. So within 1 or 2 years, that repertoire will increase if the demand for this kind of thing increases. Nobody has made triple wall nanotubes that you can buy because there's no, it's a lot of work and technology is very early stage. But double wall nanotubes will be available. See, double wall nanotubes is probably what's going to be industrialized because they have a robustness and they're rather easy to make, and you can make them with the Fullerene method, and you have quite a bit of quality control with that. Now, with today's technology, of course, that's going to increase a lot. And for commercial applications, it's more robust and more controllable, I think, than the single wall, except for the chirality aspect. So I think we'll see quite a bit of activity in the next few years from companies. I don't know companies here in Switzerland what they're interested in, but maybe.
Last question, please.
Has anyone made chloride out of nanotubes?
Not a toroid, a nanotube, but people have made toroids out of carbon. But the amount of research on toroids is very limited, but it can be done, and there is almost all the work is Japanese on toroids, but there is quite some literature. And there's also literature, some interesting, of instead of tubes, scrolls. I just refereed a paper. It's not out yet or accepted or anything like that, but people are starting to work on scrolls now. Okay, well, I bring this up because scrolls were known, and there was a very famous paper with very high citation in 1960. And since that time, there's been almost nothing on it, but until very recently. So that could be an interest. You know what a scroll is? You take a piece of paper. Here, scroll is this. You make nanotube like this. And that could be, so why is that interesting? It has an edge. So you could have edge states have chemical reactivity, and you could have diameter. So this, chemists, I think, will like that, whereas a nanotube has no reactivity, it's a closed shell. So I frankly think that that's an interesting thing to work on. That's my opinion. Okay.
Okay, so let's thank Professor Dresselhaus again for this nice talk.
I'm happy they like the talk.